All right. And I'm going to be uploading these guys. I'm sorry, like uh, that upload speed has been incredibly slow, so I've kind of fallen behind with some of the uploads. All right. So my first question, if we were back in physics 1 and I gave you a question like this, so here's the earth, like, here's the ground, so earth, and you take something like, like something heavy and you lift it up. How much, do you remember, like, how do you figure out the work? So let me back that up, edit. So I'm looking for the work. How would you calculate the work? What was that formula? And go ahead and just yell it out, guys. Guys, remember, how do you calculate the work of just lifting something up here on Earth? How would you do that?
Um, you figure out how much force you need to counteract gravity.
Yep, so force and what else? There's one more component, force times
Wait,
Distance.
distance. Yeah, so distance or displacement. We'll just say distance for now because I don't care whether it's like displacement. Oh, we don't need to worry about that. Um, so if, we know that the force that we have to apply, we know that gravity is applying a force, right, in the downward direction. And in this case, if it's just like a ball or like, a very heavy weight, if we're lifting it up slow, like very, 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 very slowly, right, we know that the work is just going to equal the weight. So the work equals mg, like the weight of the object, right? All right, so like, for this one problem in the previous physics class you had, that work, which we'll do as a capital W, and that's like, this is the work done to gravity. It's the force, which is mg, okay, times the displacement or distance, work equals mgd, okay? So this is the work done by gravity in this case. Now, let me ask you a question. You studied like, sorry, I have like Zoom pops open like 3 windows when you want to do this. Sorry, give me 1 second to move windows around here. All right, now this is energy, right? And also it's energy. All right. Now, this is one way to calculate the energy required to move something. You also talked about, so like I'm going to write this down here. Another thing that you talked about is there's energy due to speed, energy due to velocity. So that if an object's moving, that object has this thing that we call energy, and it's called like kinetic energy, right? So there's like this thing we call energy due to velocity, which we call kinetic energy. Do you guys remember a formula for kinetic energy from your previous class? I'm just gonna write it as KE for now, kinetic energy. I'll give you a hint, it starts with like a 1/2 term. Do you remember what that?
mv squared.
Very good. So there's like an object has like, if it's in motion and it has mass, it has this property called kinetic energy. And like there was this other form of energy due to position or place. Do you guys, in the context of like what we were just looking at, it starts with a P, right? What do we call that type of energy? Not position energy. Yeah, potential energy. Energy that has the potential, the ability to be converted into real energy, which would be energy of motion. So potential energy. And for whatever, well, we have a few reasons. We don't usually abbreviate potential energy as PE. We usually just abbreviate it as capital U. And the reason for that is there's 2 other terms in physics with a P. there's momentum, and then there's pressure. So like we changed the symbol for this. And on Earth, like potential energy or gravitational potential energy is mg. If you want to call it h, height above the ground. This is gravitational potential energy.
Wait, are you also allowed to write potential energy with like EMP, or is that not allowed?
EMP, what do you mean EMP?
No,
Electromotive?
no E, like a big E and then a small p. Like, are you allowed to write it that way as well, or
No,
like
like start you. Yeah, that's a good
okay?
question. Yeah, start using capital U. That's a good question, Harlito. Like definitely use capital U. And the reason for that is uh, in physics, like as in this new unit of physics. So what I'm trying to do here is we're going to start talking about the energy required to move electric charges. And so we're going to actually need, so let me just finish writing gravitational, sorry, let me just finish what I was going to write here. So gravitational uh, potential energy. So what I want to talk about today is, so I want to talk about electric. Sorry, my handwriting is just bad with this program today. It's the way I'm sitting. So what I want to talk about is electric potential energy. Okay. And the cool thing is we're going to need to talk about, and we're going to use some, this is kinetic energy, the energy something has due to how fast it's moving, okay? This is going to stay the same for us. We're going to use this formula, uh, uh, depending on our time. Yeah, we're going to use this formula today. Now, when we're talking about charged objects, in this case, when we're talking about electrons speeding up or being slowed down, we don't care about gravitational potential energy. The, don't write this down, but like you know, if you want to, you can. The electric force is 10 to the 42 times more powerful than the gravitational force. Well, let's just call it gravity. When we have charged objects and they're like, you know, they're protons and electrons, we don't care about gravity at all. Why? Because the electric force, the force on charged objects, is going to be so much bigger that like the force due to gravity is going to be insignificant. It doesn't matter anymore. All right. So I'm going to kind of flip back over to this other slide here. All right. So you have this, okay. And what this, like, if you want to call it image, so this image over here, the one that's labeled B, all right. So there's one way to talk about potential energy. We can talk about something that has gravitational potential energy. There's another form of energy that we're trying to make a comparison to, and that's electric potential energy. All right. So I'm gonna show you this more in 1 second. So we're gonna go to the slide down here just a little bit. All right, so this is a little bit of a review from last class. I drew something that looked sort of like this, all right? Charges have this property that they create. They create an electric field around any charged object. Just like Earth creates a gravitational field around objects with mass. So the analogy that we need to start thinking about is, why do things fall down on Earth? Well, we like to say, oh, things fall because of gravity. But what does gravity do? Gravity creates something we call a gravitational field, all right? Things like, you know, like two objects that are separated, they are aware of the presence of another object because each creates a field, and it's the fields around those objects that either attract each other in the case of gravity, or in the case of charged objects, you create a field that either pushes other charged objects away, so like charges push away like charges, or you have like another type of field that can attract objects, okay? So these are just two different ways that we draw what is called the electric field around an object. An important thing to bring up, here's a positive charge. When we draw the electric field around a positive charge, it always points away from the charged object. Why? It's just our convention. It's kind of like y is positive up and negative down, okay? It's a convention. With these vectors, right? So these represent the electric field vectors. The closer the, in this case, if you want to think of it as like a charge, the closer a charge is to another, the bigger the force is between the two charged objects. So we'll draw a bigger vector, okay? And if you had that same charge and you brought it way over here, well, the farther away from a charge you go, the smaller the electric force and the smaller the field that is felt by the charged object, okay? And then if you had something in between, notice that the field vectors, the electric field diagram the vector length depends on where it is, all right? The exact same thing happens with a negative charge. We draw the electric field vectors going towards the charge, y. Y is up, positive, and down, negative. It's just our convention, okay? The reason I'm bringing this up is we're going to start to think about creating an electric field. And we can do that by using a battery, using like a wall outlet, any type of power source. We can create something called a separation of charges, okay? And here's, I'm gonna go back to this other screen. So anytime you can separate charges, you create electric potential energy. So this is like probably of anything today that you need to remember, this is the most important thing to remember. Anytime charges are separated, creates electric potential. All right, and so like, what is electric potential? Well, what is gravitation, or what is gravitational potential? It's the ability of, in the case of gravity, gravitational potential is the ability for gravity to speed up an object with mass. What is electric potential? It's the ability of an electric field to speed up a charged object within that field. So like one way, so there's many ways to think about electric potential energy. One of those ways is to think it's an electric field's ability to speed up a charged object. And the symbol that I believe we introduced it last time. So like when we want to talk about electric fields, instead of writing the word electric field over and over and over again, we're just going to use a capital E. And we're going to put a little arrow over it because it's a vector, okay? So in electric fields ability to speed up or slow down charges, or slow down I'm going to use one more word in parentheses, to move, all right? So what do you do when you speed something up or slow it down? Sorry, let me back that up 1 second. Slow down. So those are like, one way to think of this is to move, to cause things to move. Slow down electric charges. All right, so like, what does an electric potential do, or what does it have the ability to do, the potential to do? To cause charges to move, to cause charges to speed up, to cause them to slow down. When you have an electric circuit, like, like a battery connected to a light bulb, you cause the electrons in the wire to move. Moving electron creates an electric current, okay? So yeah, I'm gonna write a few things down. So moving electrons And I really should just say charges. So moving electrons, an electron is a charged particle, creates an electric current. All right, so the one thing I have not done yet is, I've given you some words like electric potential. We said anytime you separate charges, you create an electric potential. And what that means is you create an electric field which has the ability to speed up or slow down electric charges, or you have the ability to move them, okay? And so like, I'll give you guys a second to copy that down, to check the time. So we have 20 minutes, if I'm correct, right? I don't want to rush anything. It's okay if I switch screens for a moment. So the thing I'm about to draw, so I'm going to try to draw this. All right, so you have this diagram in your book, and I'm just going to try to draw this to kind of to illustrate an important concept. So this is in physics we actually call this a parallel plate capacitor. That word doesn't matter for today. All I want to do is illustrate a concept. So we have these two charged plates, and we'll talk about why one is positive and one is negative, but for the purposes of today, let's just call the top one, we'll just say it's like positively charged. All right, we'll call this one positively charged. And then this one is negatively charged. Okay. And what this does is it creates an electric field between the two plates. How do we do this? We attach a battery to the plates. But what I want you to know is between these two plates, sorry, that's a bad line. Between these two plates, you're creating an electric field. And I'm just going to put like 3 of these vectors. So these are electric, or an electric field is created. Okay. Now, if you have an electric field like this, we'll call it a uniform electric field. It means it's constant. It doesn't change directions. It's just like a straight electric field. If you were to take a charged object, let's just call it like here's a positive charge. So we'll call this charge Q. We'll just use a Q for charge. Okay. If this, just intuitively, if this is positive and this side is positive, which way is this charged object going to move, up or down? Like kind of towards the positive or towards the negative? Yeah, very good, down, okay? So how do we explain that? Like we know that, just like on Earth, gravity pulls like an object with mass towards the ground. In this electric field, gravity, in this case, is going to pull this positive charge towards the negative plate. Oops, sorry. Let's do this in a different color. So we know that the electric force is going to, like, let's just use the word apply a force to this charge. So there's going to be an electric force applied to this charge while it's in this electric field, all right? So what I want to do is, like, I'm going to just go over to the side just a little bit. In the very beginning of class, we started with this equation. Like we said that work equals force times distance, okay? Now in this case, we're not talking about the gravitational force. We're talking about the electric force. So I'm going to put a little, that's supposed to be an E, but it's too small on that. Like that, okay? Now, do you guys remember what was the word? Do you remember how like an electric, remember we defined an electric field as the, F the force, the Coulomb force, like we said, that force is, one, like K times charge Q1, Q2 divided by R squared. We're not going to really worry about that much anymore. We're going to talk about the electric field, which is the force per charge, right? So like we said that if we wanted to know like the charge on if we wanted to know the force on the object, if we knew like the electric field strength, okay, we could figure out that force. So what I just want to rearrange this as, if we want to know the force on a charged object in an electric field, we can just write that as whatever the charge of the object is times the electric field, okay? How is this similar to like the work done by gravity? Well, it's like gravity equals mg. This is very similar to that. So we can rewrite this as the work equals q e d. So this is charge. Let me write one more thing. This is the work done by the electric field. So Q is the charge, E is the electric field, and in this case, it's the electric field strength. Sorry, I'm trying to squeeze that in there. Electric field strength. And then this one is like the distance that you get a charge to move. We're not going to use this form of the equation very often. So I'm going to give you guys, I wrote a lot there, so I'm going to give you guys a second to copy that down. And then then we're going to start to do some more problems, like once you have a second to write that down. I see you guys stop writing. Yeah. So like this is, and I'm gonna just, I'm gonna rewrite this just because it's getting kind of messy right there. So this is one of the two equations that we need today. So, sorry. So we need this equation, work equals QED. All right, so remember this is energy. And then the other one that I'm going to use today is work. We're going to actually write this as delta U. This is electric potential energy. This one I'm going to give you without saying what it, without showing you where it came from. We're going to write this as this. So these are two energy equations. So there's energy in an electric field, or energy to move a charge, okay? All right, and then the one thing I haven't defined is this is just like potential difference. This is like potential, electric potential, okay? And we're gonna do some examples now to try to make sense of these, all right? But the important part is What unit do we use to measure energy in? Do you guys remember? Starts with a J. What
Joules.
unit do we? Very good. We're going to use the joules. All right. So like know these two equations, okay?
Oh, there.
And I'm gonna show you how for like now I'm gonna show you how to actually use these equations. Is it okay if is it okay if I move this now? So hang on one second. Just can I change the screen? Can I? Is that it? Or do you guys still need more time to copy? Yeah. No. Okay. Okay. So check it out. Oh, one last analogy. The one last analogy. Imagine like you have like a tube, like a hose filled with water, and that hose is held up at both ends at the exact same level. Then the water should stay in the hose. But the moment one side of the hose is lowered, water is going to flow from the higher end to the lower end. Okay. And why? Gravity. Gravity pulls the water down. So the analogy that I was trying to make here is why does a positively charged object in an electric field move from the what we'll call a higher potential to a lower potential? It's the same analogy as water, right? It goes like the water has higher potential energy, goes from high potential energy to lower potential energy. The exact thing is happening with a charged object in an electric field. It wants to move from high potential energy to lower potential energy. Okay, it's analogous to like gravity. All right. So what I would like to do here is let's start doing some problems to make sense of all of these like new terms. Okay. All right. So if we look at number one, it says an electron acquires 5.25 times 10, this is like to the negative 16 joules of kinetic energy when it is accelerated by an electric field from plate A to plate B. So like from this diagram, these are just called plates sometimes, just for terminology. You're going to have an electron in an electric field, and it's going to be accelerated between two plates. Okay. What is the potential difference between the plates? All right. So I'm going to. I'm going to rewrite these equations. You don't have to write these equations yet. I just wanted to show you something here. So the equations that I just wrote is delta U. This is electric potential energy. And this is going to equal, I think I said Q, the charge, times the electric potential, the voltage. All right, this is just called voltage. So this is like one of the two equations that I wrote. And then the other one was like work equals the charge, the electric field strength, times the distance between the plates. Now, in this case, like going back to here, a few things. They give us energy. They say kinetic energy equals five. So let me kind of go back here. So that 5.25. So I'm going to write this. So they write kinetic energy, but I'm going to just write it energy for right now. So energy equals 5.25 times 10 to the negative 16 joules. And this was an electron, right? Is that right? Yeah, an electron requires this when it is accelerated by this field. What is the potential difference between the plates? All right, so charge on electron, okay? All right, this is one of those things, if you don't know, you'll learn quick just from doing a lot of problems. The charge on an electron is 1.6 times 10 to the negative 19 coulombs, okay? So what we're looking for was we were looking for the, what do they call it here? I'm gonna call it. We're looking for the potential difference, all right? The potential difference is the voltage, okay? So, should write that here. The voltage, this is the electric potential difference, okay? So what we're looking for this is we're looking for delta V. We're looking for the voltage, the electric potential difference. So I'll just write question mark. So like when you're stuck, this is what I encourage you to do. Oops, sorry. When you're stuck, what I encourage you to do is write down the equations that you know, okay? So I know that these two equations, so I know this equation and this equation relate energy and charge, okay? This one, so this one right here relates energy, this is energy, charge, and the electric field strength, all right? This one here is electric potential energy, it's still energy, charge, in the voltage, the electric potential difference, all right? So when you're like, oh, which equation should I use? Write the two equations down. See what terms match the quantity that you're looking for. So for this one, I know that delta U equals Q delta V, the voltage, okay? And what I'm looking for in this case, I'm looking for delta V. So I'm going to just rearrange the equation so that delta V equals my energy, my electric potential energy, divided by the charge on the electron. So this one right here is the electron charge. So in this case, this is going to be 5.25 times 10 to the negative 16, negative 16 joules. And that the charge of on an electron is 1.6 times 10 to the negative 19 coulombs. Can you guys do that in your calculator for me, please? And tell me what you get for a number?
I'm getting it's a weird number.
Say it again. What's the
getting-
number?
I'm getting a weird number.
Okay, like is it?
3,281.
Yeah, 3,281.25.
Okay, okay. So like, okay, that's correct. 3,281. Like, and now the units for this, a joule per coulomb is called the volt, V-O-L-T. So a joule per coulomb, like a joule per coulomb. So the energy per charge, sorry, let me make more room over here. So joule per coulomb, energy per charge. This is referred to as a volt. Another way to think of this is the energy each charge has. All right, it's going to be a volt. Now, one other thing. How many sig figs should I include in my answer? Because I'm going to start to push significant figures. So I have 1, 2 here. I have 1, 2, 3 here. How many units should I have here?
One, maybe?
No, 3. I mean 2. No, 2. 2.
Two. So like How should I round this number? What should I round that to?
3.
Yeah, so this would be like, just because we're going to start to, and I want you to practice using the correct number of significant figures. So we should write this as just 33,000, and instead of writing the word volt out, just write capital V. Okay, so make sure it's a capital V, capital V. Oh, all right, so check it out, guys. It's what, 12:45? Good. All right, so we're gonna see each other again. So what I would like you to try, okay, hang on one second, let me just go to the screen. I would like you to try not problem 2. I would like you for homework for Thursday, try to do problem 3, okay? I'd like you to try to do problem 3. And if you need assistance with it, there's a similar problem in your textbook on page. There's a similar problem on page 204 in your textbook, okay? But that's all I'd like you to do for Thursday. Just try to get that one problem done. If you haven't, hang on one second. If you haven't done, all right, there we go. If you haven't done these, if you haven't done the electric field MCQs, would you make sure you get those done for Thursday as well? All right. So if you're on in thinking or in think, you should be able to get the answers right away. All right. All right. So with that said, you guys are free to go, and I'll see you on Thursday. Okay. All right. I'll see you guys later. All right.
Thank
Goodbye.
you. Bye.
Bye.
Thank you. Bye.